A neutron star is what happens when matter is pushed too far. Not merely squeezed until its atoms sit closer together, but driven beyond the point where atoms can remain intact at all. Their electron clouds are stripped away. Their nuclei are forced into reactions that ordinary matter avoids. Protons and electrons are pressed into new arrangements. Neutrons become overwhelmingly abundant, and a mass comparable to the Sun is confined within a sphere roughly the size of a city. That sentence is easy to hear and almost impossible to picture. A city has streets, air, distance, and empty rooms. A neutron star has so little room left between its particles that familiar ideas such as solid, liquid, and gas stop being useful guides. The object has a surface that can carry mountains and crack. It has layers that can flow without ordinary friction. It has a core where the correct names for the particles may still be unknown. Yet, it is not an undifferentiated ball of neutrons. The name is true in the broadest sense and misleading in nearly every detail. The famous shortcut is the spoonful. A teaspoon-sized amount of material at a characteristic neutron star density would contain roughly 1 billion tons of mass. That comparison gives the density a human scale, but it quietly creates the wrong object. It suggests that neutron star matter is a magical substance that could be scooped out, placed on a table, and remain what it was. It could not. The matter deep inside the star exists in that state because the weight of the entire star maintains an extraordinary pressure around it. Every deeper layer is confined by everything above. Remove a small sample from that pressure, and the conditions defining the sample disappear. It would expand violently. Its particles would seek new states. Free neutrons would begin to transform through weak nuclear reactions. Neutron-rich nuclei would change as they moved toward more stable combinations. Material thrown out during a neutron star collision follows this kind of decompression, and some of it builds heavy elements through rapid captures and later decays. So the spoonful does not carry the neutron star with it. Its enormous mass is real, but its condition is not portable. The density belongs to a whole gravitational structure, not to a permanent lump with supernatural weight. Take away the surrounding pressure, and the matter changes. The honest wonder is greater than the myth. A neutron star is not made from an impossible substance placed inside gravity. Gravity and quantum matter create the substance together, moment by moment, across the entire star. The phrase neutron star matter names a condition as much as a material. Density, composition, and stability arrive as one package. The spoon can borrow the density for a thought experiment, but it cannot carry that package away. If the spoonful now feels like a condition made by a whole star, subscribing is a small way to help me keep building explanations with this much care. That dependence on pressure begins before the neutron star exists. Near the end of a massive star's life, fusion has built a central core rich in iron group nuclei. Earlier fuels released energy when lighter nuclei joined. Iron sits near the peak of nuclear binding, so ordinary fusion beyond it no longer pays the energy bill that supported the star. Burning continues in shells outside the core and adds more ash to the center. The core becomes hotter, denser, and more massive, but there is no new central fuel capable of restoring the old balance. Several forms of support are present at this stage. Heat contributes pressure. Atomic nuclei contribute through their motion and interactions. Electrons, which are fermions, fill available quantum states, and resist being confined into a smaller volume. None of these contributions is a set of tiny pillars. Pressure is the collective response of matter to compression. As the core grows, gravity demands a response that the existing state can no longer provide. Then two changes make the loss of support faster. Energetic photons begin to break iron nuclei into lighter pieces, and individual protons and neutrons. This photodisintegration consumes energy that had been helping to hold the core up. At the same time, electrons are pushed to such high energies that nuclei can capture them. An electron and a proton can become a neutron, while a neutrino carries away energy. Fewer electrons remain to provide electron pressure, and the composition moves toward neutron-rich matter. Collapse follows. The inner part of the core falls inward in a coordinated way, while outer regions fall behind it. Density rises so rapidly that neutrinos, which usually pass through a star almost untouched, begin colliding often enough to become trapped for a time. The collapsing center is no longer an ordinary stellar core. It is becoming a hot newborn object, still holding many neutrinos, called a proto-neutron star. The inward motion does not stop because neutrons form an impenetrable floor. At lower density, the quantum rule that identical fermions cannot all occupy the same state forces particles into states with greater momentum as the available space shrinks. That raises the pressure. Near and above nuclear saturation density, strong interactions between nucleons become equally essential. Interactions involving pairs and triplets of particles change the energy cost of further compression, and their repulsive response at short distances helps the pressure rise sharply. Quantum state filling supplies part of the resistance. Nuclear interactions supply another part. At these densities, separating the two into simple mechanical pieces would miss the physics that actually halts the collapse. The central region stiffens and slows. Infalling matter runs into that decelerating core, creating a shock. It is tempting to let the story end there, with a bounce that blasts the star apart. But detailed calculations do not permit that shortcut. The shock spends energy breaking heavy nuclei into nucleons. Neutrinos carry energy away. The shock usually stalls before it can escape. What may revive it is energy deposited by the flood of neutrinos emerging from the hot proto-neutron star, assisted by turbulent motion and large rising and sinking flows behind the shock. The outcome depends on the structure of the dying star, its rotation, its magnetic field, and the complicated motion of matter around the new core. Some collapsing cores produce explosions through this delayed neutrino process. Some especially energetic events may draw strongly on rotation and magnetic fields. Some fail to eject enough material and continue feeding the center until a black hole forms. Even a successful explosion does not leave a finished neutron star at once. The newborn object is hot, swollen, and rich in trapped neutrinos. Over seconds, and then longer, neutrinos escape. The star loses energy, changes its chemical balance, and contracts. Matter settles toward the cold state that can survive for millions or billions of years. If the remnant is too massive for its final pressure to support, cooling can remove temporary support and allow a delayed collapse. A neutron star is therefore not guaranteed by the first halt. It is the stable outcome only when the remnant finds a lasting balance. That balance raises the next question. If gravity has already crushed a stellar core to nuclear density, why is the result not already a black hole? A black hole is not simply matter that has become very dense. It forms when enough mass and energy are confined inside a boundary from which light cannot escape. For a given mass, there is a critical compactness. A typical neutron star, with about 1.4 times the Sun's mass, may have a radius near 12 kilometers. A black hole with that same mass would have an event horizon radius of only about 4 kilometers. The neutron star is extraordinarily compact, but its surface still lies well outside the horizon it would need to cross. Its pressure gradient is what keeps that surface there. Pressure is greatest at the center and falls outward. Each layer supports the layers above it, while gravity pulls every layer inward. This sounds like the balance inside an ordinary star, but the resemblance hides a decisive difference. The gravity is strong enough that Newton's description is no longer adequate. Their name matters less than what the equations do. Start at the center, with a chosen pressure and a rule for how the material responds. Move outward through one thin spherical layer after another. Add the mass and energy enclosed so far. Recalculate gravity in curved space. Reduce the pressure by the amount needed to support the next layer. Continue until the pressure reaches the value at the surface. The result is a mass and a radius for one possible star. The rule supplied at the beginning is the equation of state. In its simplest cold form, it connects pressure to energy density. It answers a material question. When this matter is squeezed a little more, how much harder does it push back? The word equation can make that sound settled. It is not. At densities near those in atomic nuclei, laboratory measurements and nuclear theory provide useful anchors. At several times that density, calculations become far more uncertain. The strong force is described by quantum chromodynamics, but cold matter at neutron star density cannot yet be calculated directly across the full range with the precision needed. Different physical assumptions, therefore, produce different candidate equations of state. A relatively stiff equation of state produces a large increase in pressure as density rises. It tends to support larger radii and a greater maximum mass. A relatively soft equation of state gives less pressure at the same energy density. It tends to produce smaller stars and may reach instability at a lower mass. Those words describe local behavior, not permanent labels. The same equation of state can be stiff across one density range, soften when new particles appear, and stiffen again through repulsive interactions at greater density. For every candidate rule, the relativistic balance calculation generates a curve of possible masses and radii. Low-mass stars occupy one part of the curve. Increasing the central pressure moves along it toward heavier, denser stars. Eventually, the sequence reaches a maximum mass. Beyond that turning point, adding central density no longer produces another stable version of the same kind of cold, non-rotating star. A small inward disturbance grows instead of being restored, unless another stable branch exists. Because the material changes phase, collapse follows. There is no universal number for that limit, because the limit is one of the things the unknown equation of state determines. Rotation can raise it. Heat and trapped particles can raise it temporarily in a newborn star or a merger remnant. differential rotation can support a merger remnant that no uniformly rotating cold star could match. As angular momentum and heat are lost, that temporary star may cross its changing limit and collapse. Calling every such threshold the neutron star limit would hide those distinctions. Nature has supplied an unforgiving lower test. Radio timing has revealed neutron stars with masses around twice that of the Sun. The especially well-measured pulsar called J0740 plus 6620 has a mass close to 2.08 suns. Any proposed equation of state that fails before reaching such a star is not an equation of state for the universe that contains it. This does not prove that the core contains only neutrons and protons. It means that any additional particles or phases must still permit enough pressure at high density to hold up the observed mass. Radius adds a different kind of leverage. Around a mass near 1.4 suns, the radius is especially sensitive to pressure in matter around 1 to 2 times nuclear saturation density. The maximum mass reaches deeper into the uncertain high-density response. A heavy star's radius can connect those regimes. Each reliable mass and radius pair marks a region on the same diagram, and a valid equation of state must thread its curve through all of them at once. This is why a difference of a kilometer matters. Against a radius near 12 kilometers, 1 kilometer is not a decorative correction. It changes the allowed pressure of matter no laboratory can hold. Yet it cannot be interpreted by a slogan alone. A small inferred radius may favor softer behavior through part of the star. A large maximum mass demands enough stiffness somewhere deeper. The combination may indicate a gradual change in nuclear forces, the onset of new particles, or a transition between phases. Several microscopic stories can draw nearly the same mass and radius curve. The curve constrains the response of matter before it uniquely identifies the matter itself. The structure beneath the surface shows why. Moving inward is not a descent through familiar substances arranged like rock, water, and metal. It is a sequence of quantum reorganizations driven by rising pressure. The boundaries are not all sharp, and their exact depths depend on mass, temperature, magnetic field, history, and the still uncertain nuclear interaction. Even so, the broad order is one of the best established parts of the star. At the top lies an atmosphere so thin that it contributes almost nothing to the total mass. Its particles determine the spectrum of radiation that escapes, so this negligible mass can dominate what a telescope infers. Gravity separates elements efficiently, allowing the lightest available species to float to the top unless magnetic fields, accretion, or ongoing particle bombardment complicate the composition. Hydrogen is often assumed for a pulsar that has accreted matter from a companion, but helium or heavier elements can change how radiation is beamed and therefore change an inferred radius. Beneath the atmosphere, depending on temperature and accretion history, there may be a fluid ocean. Continue downward and the ions freeze into the solid outer crust. The word solid is deserved because the nuclei occupy an ordered lattice held by electrical forces and can resist shear. It is still unlike any solid on Earth. Electrons are no longer attached to individual atoms. They form a highly degenerate, nearly uniform background moving through the lattice. Much of the outer crust's pressure comes from those electrons. As depth increases, the electron momentum rises. electron captures become energetically favorable, converting protons inside nuclei into neutrons, and driving the nuclei farther from the combinations found in ordinary matter. The lattice does not consist of one kind of nucleus from top to bottom. It passes through a sequence of increasingly neutron-rich species. At the greatest outer crust densities, many of those nuclear masses have never been measured in a laboratory, so models must extend beyond known isotopes. The existence of the lattice is secure. Its exact census is not. Near a density of about 400 billion grams in each cubic centimeter, a new threshold is crossed. Inside a nucleus, a neutron occupies a bound quantum state only while adding it lowers the total energy. With enough neutron excess, the next available neutron state is no longer confined to one nucleus. Neutrons begin to occupy extended states through the material. This is neutron drip. Nothing drips downward. Gravity has not pulled beads of neutron liquid from the nuclei. The name describes a binding threshold. Below it, neutrons are bound within distinct nuclei. Above it, some neutrons are unbound and can move through the lattice. The outer crust has become the inner crust. The inner crust is one of the strangest known forms of organized matter. Neutron-rich nuclear clusters remain arranged in a lattice. Degenerate electrons maintain charge balance. An unbound neutron fluid fills the space among the clusters. At the low temperatures of a mature neutron star, many of those neutrons are expected to pair and form a superfluid. A superfluid is not merely a liquid with very low ordinary friction. It is a coherent quantum state. Rotation cannot be distributed through it in any arbitrary smooth pattern. It is carried by quantized vortices, each holding a fixed unit of circulation. A rotating neutron star may contain an immense array of these microscopic vortices. Their motion and their interaction with the crust are central to leading explanations for pulsar glitches. The sudden small increases in rotation seen in some stars. That does not turn every glitch into a direct map of the inner crust. Vortices may couple to matter in the core as well. Neutrons moving through the lattice can be entrained by its periodic structure, reducing the amount of freely available angular momentum. Several competing models can reproduce parts of the observed behavior. The glitches are strong evidence that superfluid dynamics matters. They do not reveal one simple hidden mechanism. Deeper in the inner crust, the clusters grow and crowd together. Near the base, nuclear attraction favors keeping nucleons together, while the electrical repulsion among protons resists the formation of very large charged regions. Surface energy adds another cost. None of these tendencies can win everywhere at once. Calculations often find that the compromise produces elongated rods, broad slabs, cylindrical voids, and other complex shapes. These phases are called nuclear pasta. Rods invite the name spaghetti. Slabs invite lasagna. The labels are memorable because the geometry is real within the models, but they can make the claim sound more settled than it is. No telescope has imaged these structures. Different nuclear interactions predict different sequences, thicknesses, and sometimes no broad pasta layer at all. The defensible claim is that frustrated nuclear and electrical forces near the crust base make non-spherical structures plausible, perhaps likely. The exact menu remains theoretical. Pasta, if present, is not decorative. Geometry can change how electrons, heat, neutrinos, and magnetic fields move through the crust. It may affect how the crust cools after accretion, how stresses build before a fracture, and how the crust couples to the rotating fluid beneath. A pattern at a scale far smaller than an atom can influence signals measured across interstellar distance. That connection between microscopic arrangement and astronomical behavior is the recurring logic of the entire star. At roughly half nuclear saturation density, separate clusters cease to be favored. Their boundaries blur and then disappear. The solid crust gives way to a more nearly uniform fluid core. This transition is not known at one universal density. It depends strongly on the symmetry energy, the part of nuclear physics that sets the cost of having many more neutrons than protons. Still, the change itself is expected. Matter can no longer lower its energy by maintaining isolated nuclear islands. The outer core contains most of the star's volume and much of its mass. It is often described as neutron matter, but that phrase again needs repair. Neutrons dominate, yet a stable cold core also contains a small fraction of protons and a balancing population of negatively charged leptons. Electrons appear first. At greater density, the electron energy becomes high enough for muons to join them. The composition is governed by beta equilibrium. A neutron can transform into a proton while producing an electron and an antineutrino. A proton and an electron can combine in the reverse direction. In an old transparent star, neutrinos escape, so the surviving mixture settles where the relevant chemical energies balance. Electrical charge balances too. The star is not built with a large net negative or positive charge. The number of protons is matched by the combined negative charge of electrons and muons. Representative calculations give a proton fraction of only a few percent in part of the outer core, often around 5% near characteristic densities, though it changes with depth and with the nuclear symmetry energy. That small fraction matters enormously. It controls which neutrino-producing reactions are possible. It affects cooling. It supplies charged particles that couple the fluid to the magnetic field. It prevents the accurate description of the core as a pure neutron sea. Nor are the particles tiny hard spheres pressed shoulder to shoulder. Their quantum waves overlap, and each particle moves in response to many neighbors at once. A picture of neutrons merely touching misses both the quarks inside each nucleon and the fields carrying the strong interaction. Pairing may reorganize this fluid. Neutrons and protons can form pairs that move as one quantum state. Neutron pairs make a superfluid. Because protons carry charge, proton pairs also make a superconductor, able to carry current without ordinary electrical resistance. Depending on its form, that superconductivity can confine magnetic field into narrow tubes or redistribute it more broadly. The broad expectation of neutron superfluidity and proton superconductivity is grounded in nuclear theory and supported indirectly by stellar cooling and rotational behavior. The details are much less certain. The energy needed to break those pairs depends sensitively on density and on the interaction used in the calculation. A given species may be paired across one region and unpaired deeper down. Magnetic fields may alter the proton state. Vortices in neutron superfluid can interact with magnetic flux structures, linking rotation, magnetism, and thermal evolution in ways that remain difficult to calculate. Pairing should not be recruited as a new version of the support myth. Superfluidity changes heat capacity, neutrino emission, rotational coupling, and transport. It does not replace the bulk equation of state with frictionless strength. The pressure holding up the star still comes from the full energy response of dense matter, including fermion motion and strong interactions, all balanced through general relativity. Then comes the least secure boundary in the entire cutaway. There may be a useful place to call the beginning of an inner core, but there is no observed line and no agreed composition waiting beneath it. The distinction means that density has risen beyond the range where a description using only familiar nucleons and leptons can be trusted without serious doubt. What changes when a new particle becomes possible? Matter gains another way to arrange the same energy. That can let density rise without pressure rising as quickly, although new repulsion may later restore the pressure. One possibility is that the same basic particles persist. Neutrons, protons, electrons, and muons could remain the relevant degrees of freedom while their interactions become increasingly complicated. If repulsive, many body forces grow strongly enough, nucleonic matter can support heavy stars. This is the conservative picture, but conservative does not mean demonstrated. Laboratory experiments do not reproduce cold, electrically neutral matter at several times nuclear saturation density, and theoretical expansions that work lower down eventually lose control. Another possibility is that hyperons appear. They are heavier relatives of protons and neutrons that contain strange quarks. Once compression makes creating them cheaper than forcing ordinary particles into still higher energy states, they can enter the matter and often soften it. Extra repulsion must then restore enough pressure to support heavy stars. Pions or kaons might instead share one organized quantum state and help carry charge. Models disagree about whether stable stars reach those conditions. At greater density, quarks may move through the material rather than remain confined inside separate protons and neutrons. This would be cold, dense quark matter, not the hot plasma made briefly in collisions. It could appear abruptly with a jump in density, or gradually as the old and new descriptions blend. The unresolved question is whether stable neutron stars become dense enough for either route. Current analyses do not agree, because none observes a core directly. They connect lower density nuclear evidence to higher density theory through different mathematical bridges. One bridge can favor quark-like behavior, while another leaves nucleons sufficient. A sharp transition may fit one combined data set and fall beyond the stable stars in another. The disagreement marks the reach of the assumptions. The honest center is therefore a field of constrained possibilities. It must provide enough pressure to support heavy pulsars. It must not produce radii or tidal responses inconsistent with observation. It must join smoothly, or through a physically allowed transition, to the better understood matter outside. It must respect causality, so disturbances do not outrun light. Within those boundaries, more than one composition survives. That uncertainty does not make the interior arbitrary. Every layer has to carry the same gravitational burden. A softer region changes how quickly pressure grows. A phase transition changes density and compressibility. A new particle changes heat capacity and neutrino cooling. Superfluid gaps alter the rates at which the star loses energy. The hidden microphysics keeps sending consequences outward. There is no probe that can be lowered through the atmosphere, no sample that can be returned without changing, and no light escaping directly from the core. The center is sealed by kilometers of opaque matter. Yet the star cannot conceal what that matter does to its global shape. The equation of state sets the radius for a given mass. Compactness bends light, leaving the surface. Rotation imprints speed and shape. Hot regions sweep beams across distant detectors. Cooling carries the memory of particles and pairing below. The interior must reveal itself indirectly, translated into signals at the surface. Those surface signals turn the sealed star into its own experimental instrument. The star turns, slows, jumps, cools, and sometimes throws out a flash powerful enough to disturb instruments across the solar system. Each change reaches Earth as light, radio waves, X-rays, or a shift in timing. The challenge is to read that instrument without pretending it says more than it does. A pulse can reveal rotation without revealing how the pulse was made. The task is to determine what changed at the surface, then ask what had to happen inside for the surface to behave that way. That method began with a mark on paper that did not look important enough to announce a new kind of star. In 1967, Jocelyn Bell Burnell was a graduate student at Cambridge. She had helped build a radio telescope spread across about 4.5 acres. Its purpose was to study quasars, distant bright objects whose radio light flickers as it crosses the solar wind. The telescope did not produce a polished image. Pens traced signals across long rolls of chart paper. Bell Burnell inspected those charts by hand, learning the ordinary signatures of distant sources, local interference, and faulty equipment. On August 6th, a small patch looked wrong. It was not a clean pulse train. It was a little patch of irregular ink, later remembered as scruff. The source appeared in the same part of the sky, but the first records were too slow to show what the signal was doing. A faster recorder was needed. Then the source disappeared for weeks. Nothing about that sequence guaranteed a discovery. The decisive act was continuing to check. On November 28, 1967, the source returned while the faster recorder was running. The paper showed a string of narrow pulses separated by about 1 1/3 seconds. Local machinery could make regular radio noise, but this signal followed the sky. It appeared when one particular celestial position crossed the telescope. A transmitter on Earth would not keep sidereal time, the slightly shorter daily rhythm set by the turning Earth and the distant stars. The pulses also remained remarkably steady. Their regularity was strange enough that an artificial source had to be considered, but one source could not decide the matter. Bell Burnell searched the charts and found more. Nature was repeating the trick in different directions. That transformed an odd signal into a new population of astronomical objects. By the time the first paper appeared in February 1968, the source known as CP1919 had become the first published pulsar, a name formed from pulsing radio source. The first paper did not claim that the case was finished. It considered rapid vibrations in a white dwarf, the compact leftover core of a lower mass star, or in a neutron star. That caution matters because a periodic signal does not automatically reveal the motion that produced it. A bell can pulse because it vibrates. A lighthouse can pulse because it turns. Both can place bright intervals between dark ones. The way to choose is to ask which mechanism can preserve the observed rhythm while fitting the extreme speed. Thomas Gold argued that rotation supplied the answer. Franco Pacini had already explored how a rapidly rotating, strongly magnetized neutron star could release energy. Gold connected rotation directly to the newly discovered pulses. A neutron star could turn with extraordinary steadiness. Its magnetic axis could point in a different direction from its rotation axis. Radiation tied to the magnetic structure would then sweep through space. Earth would receive a pulse whenever the moving beam crossed the line of sight. The star would not be switching on and off. The beam would be passing by. A lighthouse gives the right geometry, but only the geometry. It does not explain the radio light as a literal lamp fixed to the surface. Around a neutron star, intense electric and magnetic fields pull charged particles into a magnetosphere, the region of moving plasma controlled by the magnetic field. Plasma is matter in which electrons and atomic nuclei move separately rather than remaining bound into neutral atoms. The rotating field drives particles to high energies, and some of those particles produce tightly directed radio emission. Exactly where that coherent radio emission forms, how the particles organize so that their waves reinforce one another, and why some pulsars change or stop their radio output remain open questions. The beam sweep is well supported. The detailed radio engine is not complete. That boundary is useful. It allows the pulse to serve as a rotation marker even when the microscopic process that made the radio wave is uncertain. Once each pulse marks a turn, the star becomes a clock. Not a clock because its period never changes, but because every small change can be measured against a long sequence of earlier ticks. Astronomers predict when a pulse should reach a telescope, then compare the prediction with the arrival. An early pulse means something sped the apparent clock. A late pulse means something slowed it or lengthened the path. Earth moves around the sun. The pulsar may move through the galaxy, and a companion star may pull it around an orbit. Each motion leaves a different pattern in the arrival times. Even gravity can delay a pulse when the radio wave passes through strongly curved space near a companion. The signal crosses the hidden system and returns carrying a record of motion. Timing does not require a photograph of the orbit. It reconstructs the orbit from the changing travel time of the ticks. The steadiness becomes most startling among millisecond pulsars. Old neutron stars that have been spun faster by matter transferred from a companion. The fastest confirmed example is the pulsar known as J1748-2446, AD, in the globular cluster Terzan 5. It turns 716 times each second. One rotation takes about 1.396 milliseconds. A millisecond is 1,000th of a second. During an ordinary blink, this star can complete scores of turns. The number is not merely a speed record. A star that is too large or too loosely held together would shed material from its equator when spun that fast. The continued existence of the pulsar therefore rejects some combinations of mass and radius. Yet the record does not reveal the exact breaking point. Its own mass and radius are not known precisely, and different interior materials can support different shapes and speeds. 716 turns per second is an observed fact. A universal speed limit for neutron stars is not. Most pulsars gradually slow because their rotating magnetic fields and particle winds carry energy away. Their pulse periods lengthen by tiny, predictable amounts. That made the Vela pulsar especially useful. Vela is young, bright in radio waves, and normally follows a measurable slowing trend. In early 1969, its rhythm broke the rule. Between observations, the star began turning faster. The fractional increase was about 2 parts in a million. That sounds small until the clock is considered. The entire visible rotation rate of an object heavier than the Sun changed abruptly. Astronomers named such an event a glitch. The word is modest. The physical event is not. Something beneath the surface had stored angular momentum, the quantity that keeps rotating matter in motion, then passed part of it to the crust. The layered interior already supplies a candidate reservoir. Its neutron superfluid carries rotation in quantized vortices. If some vortices pin to the crustal lattice, while the crust slows, the hidden fluid keeps more of its spin. The visible clock and the reservoir drift out of step. Eventually, the difference can become too large for the pinning to hold. Vortices move, and a disturbance may free many more. As vortices shift outward, the superfluid gives angular momentum to the crust. The radio clock jumps forward. This vortex picture explains why glitches can be sudden, why they are followed by several stages of recovery, and why a star can repeat them after rebuilding the difference in rotation. It also turns one tiny timing change into evidence for a state of matter. No telescope sees a vortex. The evidence comes from the amount of angular momentum transferred and the way different parts of the star reconnect to the new rotation rate. In the Vela pulsar, decades of glitches show that a persistent hidden reservoir is involved. The best developed explanation is superfluid neutrons, whose vortices can pin and release. The clock can now be watched more closely than it could in 1969. During a Vela glitch in December 2016, continuous observations captured changes around the event. Later analysis constrained the main rise to less than 12.6 seconds with 90% confidence. The frequency briefly overshot part of its later path, then changed again as internal components exchanged angular momentum. That overshoot is hard to reproduce with a single crust and a single hidden fluid. It points towards several components connecting on different timescales. Some may follow the crust almost immediately. Others may take seconds, minutes, or longer. A change in pulse shape was also observed near the glitch, suggesting that the magnetosphere reacted while the interior rotation changed. The star did not provide a clean window through the crust. It provided a sequence. Each stage removed some possible couplings and left others alive. How much hidden fluid must participate? The long record of Vela glitches gives an angular momentum budget. The reservoir must contain at least about 1.4% of the total moment of inertia of the star under a standard set of assumptions. Moment of inertia describes how strongly the distribution of mass resists a change in rotation. A small fraction can be enough if it rotates slightly faster than the crust for long enough. Early calculations suggested that superfluid in the inner crust could supply the needed share. Then a complication appeared. Neutrons moving through the crustal lattice are not all freely independent. The periodic arrangement of nuclei can make part of the superfluid move as though it has been dragged along. This effect is called entrainment. Entrainment reduces the amount of freely available angular momentum in the crustal reservoir. With strong entrainment, the required crustal share can rise towards 7%. Some calculations then conclude that the crust is not enough and that superfluid in the core must join the transfer. Other calculations find that a sufficiently thick crust can still supply the budget, especially for a lower mass neutron star and a suitable relation between pressure and density. The disagreement is not a weakness to hide. It is the experiment working. The observed glitch sets a demand. Nuclear calculations decide how much superfluid a proposed crust can provide. Models that cannot meet the demand fail. Models that can remain possible. Vela therefore gives strong evidence for a superfluid reservoir, but it does not yet say with certainty where the reservoir ends. The clock jump reveals hidden motion. The crust against core question waits on better knowledge of the mass, radius, and interior forces of the star. Rotation is only one surface signal. Heat carries a different message, because heat can leave regions that radio pulses never sample. A young neutron star is born extremely hot. Its dense interior loses energy, mainly through neutrinos, nearly massless particles that interact so weakly that they escape from deep inside. Photons take a difficult route through dense matter and finally emerge from the surface. Neutrinos can carry energy away from the core much earlier. A cooling star can therefore act as a test of reactions occurring where light cannot travel freely. The difficulty is that a telescope does not place a thermometer on the crust. It measures an X-ray spectrum, the distribution of arriving light across energy. Scientists must infer a surface temperature by modeling the thin atmosphere that reshapes that spectrum. The compact object at the center of the Cassiopeia A supernova remnant offered an unusual opportunity. The remnant is only about 3.5 centuries old, making its neutron star very young by stellar standards. Chandra, an orbiting X-ray observatory, returned to it across years. An early analysis compared 9 years of observations and fitted the spectrum with a carbon atmosphere. The inferred surface temperature fell from about 2.12 million Kelvin in 2000 to about 2.04 million Kelvin in 2009. That was a decline of about 4%, while the observed X-ray flux fell by about 21%. A 4% temperature change across 9 years is astonishingly fast for a star. The event seemed to place a core process on a human career scale. One explanation connected the fall to superfluidity. Neutrons can form pairs, much as electrons pair in a superconductor, a state in which paired electric charges move without ordinary electrical resistance. The forces and environment in a neutron star are different. Below a critical temperature, many neutron pairs enter an organized quantum state. During the transition, pairs continually form and break. Those changes can release neutrino pairs, opening a temporary channel that carries energy from the core. Models found that an onset near 500 million Kelvin could reproduce the reported rapid cooling if protons in the core had already become superconducting. In this picture, Chandra had not merely measured a cooler surface. It had caught the interior crossing a phase boundary, the point where matter changes its collective state. But a surface spectrum is not a direct view of a phase boundary. Chandra detectors change with time. A layer of contamination can build on an instrument filter and absorb some X-rays. Bright compact sources can also produce pileup, in which more than one arriving photon is registered as a single event. The assumed amount of gas between Cassiopeia A and Earth changes the inferred spectrum too. a different observing configuration, chosen to reduce some of those distortions, did not find a statistically significant temperature decline across 8.5 years. It placed upper limits of a few percent per decade, with the exact result depending on whether the intervening absorption was allowed to vary. The same star had become a counterexample to an easy story. If the inferred cooling rate changed with instrument setup, how much belonged to the star and how much belonged to the measurement? Longer records have not returned the answer to the original simple form. A separate Chandra detector followed the source across about 25 years and found a decline, but a smaller one. The inferred rate was about 0.57% per decade when the intervening absorbing column was held fixed, and about 1.11% per decade when it was allowed to vary. Analyses using the other detector have generally produced larger rates. That does not make the star useless. It makes the uncertainty measurable. Different detectors, atmosphere assumptions, absorption choices, and calibration histories can be compared against the same object. A genuine decline appears increasingly supported, while the exact slope remains sensitive to the method. The safe conclusion is narrower than the most exciting one. Cassiopeia A has provided evidence of surface cooling over a period short enough to follow across a scientific career. Young neutron stars are expected to lose much of their heat through neutrinos from the interior. A transition into neutron superfluidity can explain a rapid episode and remains an important candidate. Yet no neutrinos from this star were detected, and the surface decline does not uniquely select that mechanism. Other cooling reactions, delayed thermal changes, atmosphere behavior, and calibration effects must be tested. The star is a thermometer only after its atmosphere and the instrument have been modeled. Even then, it measures the surface while the desired answer lies in the core. The value of the experiment comes from connecting those layers with predictions that can fail. Some neutron stars refuse the slow language of cooling curves. They announce magnetic stress through bursts. These objects are called magnetars because their behavior is powered by magnetic fields far stronger than those of most radio pulsars. The field cannot be held like a bar magnet for inspection. Its large-scale strength is inferred mainly from rotation and slowing. If a star loses rotational energy through a magnetic torque, a measured period and rate of slowing imply a dipole field, a broad field with two opposite magnetic poles. For the soft gamma repeater, known as SGR 1806-20, a period of about 7.47 seconds, and a rapid slowdown led to an inferred surface dipole field near 800 trillion Gauss. Soft gamma repeater is the historical name for a source that emits repeated bursts of energetic light. Gauss is a unit of magnetic field strength. The field value is a model-based inference, not a direct reading of the internal field. The inner magnetic structure could be stronger and far more tangled. The important difference from an ordinary rotation-powered pulsar is the energy account. Some magnetars shine or burst with more power than their loss of rotational energy can supply. Magnetic energy must be paying the bill. As the internal field evolves, it can push sideways on the solid crust and twist the external magnetosphere. Stress can accumulate until the crust yields or the magnetic configuration changes abruptly. Charged particles then race through the rearranged field and produce X-rays and gamma rays. A short burst reveals the release, but not a single unique trigger. Crust failure can disturb the field. A magnetospheric instability can push back on the crust. In a system coupled by an enormous magnetic field, cause and response can chase each other across the surface and through the interior. On December 27, 2004, SGR 1806-20 produced the brightest giant flare yet recorded from a magnetar. The initial spike lasted about 0.2 of a second and saturated or overwhelmed several instruments. A historical estimate placed its isotropic equivalent energy near 2 × 10 to the power of 46 ergs. Isotropic equivalent means the energy the flare would have carried if it had shone equally in every direction. The estimate was around 100 times the energy assigned to the 2 earlier giant flares. It depended strongly on the distance then assumed for the source, so it should not be treated as a distance-free measurement. The crucial observed structure came after the spike. A fading tail continued for several minutes and brightened in step with the rotation of the star. Embedded in that tail were faster, repeated changes in brightness. Those repeated changes are called quasi-periodic oscillations. Quasi-periodic means that a pattern favors a frequency without behaving as an infinitely precise clock. Signals appeared near 18 Hz, 30 Hz, and 92.5 Hz. Other analyses found features near 150 Hz, 625 Hz, and 1840 Hz, with still weaker candidates elsewhere. Hertz means cycles per second. The flare tail therefore carried a chord, from tens of changes each second to well over 1,000. The frequencies appeared at particular rotational phases and during limited intervals. They were not simply the 7-second spin of the star. Something excited by the flare was changing the X-ray output much faster. The appealing interpretation is a starquake. A solid crust can twist and shear, with neighboring layers sliding sideways relative to one another. A sudden magnetic rearrangement could strike the crust and excite global torsional motion, a twisting oscillation around the star. Different patterns would have different frequencies, rather as different vibration patterns of an object produce different notes. If each observed frequency could be matched to a crustal mode, the chord might reveal crust thickness, stiffness, and composition. That would turn a flare into seismology, the study of an unseen interior through vibrations. Earth scientists use earthquake waves in a related way. The neutron star version is harder because the magnetic field is not a passive observer. It supplies enormous tension and threads both crust and core. Disturb the crust, and the field carries the disturbance into the fluid beneath it. Waves can travel along magnetic field lines through the core, reflect, couple back to the crust, and form combined magnetoelastic motions. Magnetoelastic means that magnetic tension and material elasticity both control the movement. A frequency that once looked like a pure crustal note may instead belong to the coupled star. Field geometry, field strength, superfluid motion, superconducting protons, crust stiffness, and the place where the X-rays are modulated can all shift what appears at the telescope. Several different interiors can produce similar frequencies. Several different motions can emphasize the same band. The oscillation chord is observed. The claim that each note has already been assigned to a precise internal layer is not. Another magnetar giant flare carried its own preferred frequencies. That repetition makes an explanation tied to one detector less satisfying, while the differing notes resist a single simple tuning rule. The useful question is not whether the star rang. Its X-ray brightness plainly carried preferred frequencies after violent magnetic events. The useful question is which combination of crust, core, and field rang together. The answer could reveal the interior, but only after models explain why particular motions become visible in the radiation. Magnetars then produced a signal that connected their bursts to a mystery far beyond the galaxy. A fast radio burst is an intense flash of radio waves lasting only milliseconds. Most known examples arrive from distant galaxies and release so much radio energy that their sources were uncertain for years. Magnetars were leading candidates, but an association required more than a resemblance. It required a radio flash and a magnetar outburst from the same place at the same time. On April 28, 2020, the Galactic Magnetar SGR 1935 plus 2154 supplied that test. One radio telescope operating across hundreds of megahertz detected a burst with two main components. An independent experiment at higher radio frequencies also recorded it. In the lower radio band, the estimated emitted energy was about 3 times 10 to the power of 34 ergs. The event was thousands of times more energetic than earlier millisecond radio bursts from galactic sources, yet about 40 times less energetic than the weakest extragalactic fast radio burst known at the time. It occupied the gap rather than matching either population perfectly. High-energy satellites saw the partner event. The X-ray signal lasted roughly 0.6 of a second and contained 3 narrow peaks. The brightest X-ray peak followed one of the radio peaks by about 6.5 milliseconds, within an uncertainty of about 1 millisecond. That close timing and common sky position tied the radio flash to a known magnetar outburst. Distance still affected the inferred energy, and the radio measurements did not agree on every detail because the burst spectrum varied strongly with frequency. None of that removed the central result. A galactic magnetar had produced a millisecond radio flash, energetic enough that, if placed in a nearby external galaxy, it could resemble an ordinary fast radio burst. The exact inference is powerful because it is limited. At least some magnetars can produce fast radio burst-like emission. A magnetar outburst can generate a radio flash and an X-ray burst within milliseconds of one another. The event does not prove that every fast radio burst comes from a magnetar. It does not prove that all magnetar radio bursts use one mechanism. It does not even decide whether the decisive action occurred close to the surface, farther out in the magnetosphere, or in a shock driven into surrounding plasma. The timing gives theorists a narrow causal window. The difference in energies and the double radio structure give models targets. The event identifies a capable source class without closing the case on the entire population. It also shows the limit of surface signals in a new way. The burst carried information about magnetic energy release and particle motion outside the star. It did not pass through the core like a probe. A crust failure might have launched the event, but a magnetospheric rearrangement might have done so without a large fracture. The X-rays and radio waves reveal that linked processes occurred. They do not provide a unique map from the observed peaks back to one internal material. Across every case, the surface signal changes before the hidden mechanism is fully known. Pulses reveal rotation, glitches reveal a reservoir, cooling reveals heat loss, and flares reveal magnetic motion. Each narrows the interior possibilities, but several candidate materials can still imitate one another. That is the next wall. To separate the surviving interiors, scientists must weigh the star and measure how much space its matter occupies. Mass and radius turn the hidden pressure response into a test. Mass and radius are not merely entries in a catalog. Together, they describe how hard a neutron star is pushing back against its own gravity. A large mass packed into a small radius means matter has yielded more easily. The same mass spread across a slightly larger radius means pressure has resisted compression more strongly. So the problem now changes shape. The unseen core cannot be reached with a drill, but it leaves two numbers at the surface, and those two numbers carry news from every layer below. Mass came first, because nature provides a clock accurate enough to weigh a star across empty space. A pulsar sends radio flashes with a rhythm that can be followed for years. If that pulsar circles another star, its pulses arrive early when it moves toward Earth and late when it moves away. The changing arrival times map the orbit. The orbit reveals how the two bodies share their motion, which places limits on their masses. This is the same underlying idea that lets the motion of a planet reveal the pull of its star, except the clock is carried by one of the orbiting bodies and announces its position with every turn. Some systems offer a second effect that is especially valuable. When the pulsar passes behind its companion, each radio pulse travels through the companion's gravitational field before reaching Earth. Curved spacetime makes that route take a little longer. The delay is tiny, but the pulsar clock is steady enough for the extra travel time to appear as a repeated bulge in the timing record. The shape of that bulge depends on the companion's mass and on the tilt of the orbit. Once those quantities are known, the rest of the orbital timing can reveal the pulsar's mass. This is called Shapiro delay. The name can make it sound like an obscure correction, but its physical meaning is simple. A radio pulse passes through a deeper part of a gravitational valley and arrives later than it otherwise would. Measure the delay, reconstruct the valley, weigh the bodies that made it. That is how radio timing weighed the heavy pulsar already used as a pressure test. J0740 plus 6620 has a mass near 2.08 suns. Any candidate interior that collapses before that mass fails. Mass sets the floor. Radius became the next prize. A neutron star has no solid edge that a camera can outline from Earth. Its angular size is far too small. Even the nearest examples appear as points. Radius must be inferred from what the star does to light as it rotates, and that requires a second kind of clock. The neutron star interior composition explorer, known as NICER, watches X-ray photons from a perch on the International Space Station. It records the energy and arrival time of individual photons. For certain pulsars, small regions near the magnetic poles are hotter than the surrounding surface. As the star turns, a hot region rotates into view, brightens, moves across the visible face, and turns away. The arriving photons build a repeating pulse shape. At first, this can sound like measuring the size of a lighthouse by watching its flash. That would be difficult, even in ordinary space. Near a neutron star, gravity reshapes the view. Light leaving the far side does not always travel straight away from the observer. Space-time is curved so strongly that some of those photons bend around the star and reach Earth. More than half of the surface can be visible at once. A hot spot can remain partly visible after ordinary geometry says it should have disappeared beyond the limb. This fills in the dim portion of the pulse. A more compact star bends light more strongly, so the amount of filling carries information about the ratio of mass to radius. Motion changes the signal too. A spot sweeping toward the observer is boosted differently from a spot moving away. The photon energies are shifted by the motion and by the climb out of the gravitational field. The star is not perfectly spherical when it spins. The hot regions may not be circular, may not be equal, and may not sit directly opposite each other. A veil of X-rays may also arrive from magnetospheric particles rather than the heated surface. The measured radius, therefore, does not drop out of the pulse like the answer on a ruler. Researchers propose a physical description of the star, including its mass, radius, spot shapes, spot temperatures, viewing angle, background, and additional emission. General relativity predicts how photons would travel from that proposed star to the detector. The predicted pulse is compared with the observed one. Many possible descriptions are explored. The combinations that reproduce the data well form a credible range. This distinction is essential. NICER directly measures photon energies and arrival times. Mass and radius are inferred through a model of how the surface and surrounding emission produced those photons. The inference can be powerful without being model-free. The heavy pulsar J0740 is especially useful because its mass is already constrained by radio timing. The pulse profile then has less freedom to trade mass against radius. Analyses have placed its radius near 13 kilometers, with uncertainty broad enough to include somewhat smaller and larger stars. That result is compatible with matter that is neither extraordinarily soft nor extraordinarily stiff through the densities sampled by the star. Another nearby pulsar, J0437-4715, shows why the modeling choices must remain visible. One analysis of its NICER observations inferred a radius around 11 1/3 kilometers, with a credible range extending by roughly a kilometer around that value. A later analysis, using different spot and emission models, included a pulsed, non-thermal X-ray component, in addition to the thermal surface emission. With that component included, the same underlying NICER observations supported a symmetric 68% credible radius range from about 11.9 to 15.5 kilometers. The underlying observations did not change. The question asked of them became more complete. Some of the modulation that might otherwise be assigned to a moving hot surface could also come from pulsed emission in the magnetosphere. Once that additional source is allowed, different combinations of spot geometry and stellar compactness can reproduce the pulse. The radius information becomes less narrow. This is a useful picture of inference under extreme conditions. Imagine hearing a repeating tone through a wall. If the model contains one instrument, every change in loudness must be explained by that instrument turning or moving. If a second instrument may be sounding in step with the first, the same recording admits more than one arrangement on the other side. Nothing about the recording becomes worthless. The honest range simply reflects the newly admitted possibilities. No single radius analysis should therefore be treated as the final outline of a neutron star. Different choices for atmosphere, spot shape, background and magnetospheric emission can shift or widen the answer. Independent teams can work from the same photons and learn how sensitive the result is to those choices. The disagreements between credible ranges are not noise to be hidden. They reveal which assumptions still control the measurement. Taken together with radio masses, gravitational wave limits, nuclear experiments, and other astrophysical observations, current analyses often favor radii near 12 kilometers for a neutron star around 1.4 solar masses. The exact value remains dependent on the model and on which data are combined. 12 kilometers is a useful scale, not a universal tape measurement. A neutron star of a different mass can have a different radius, and a strong phase change inside the core could alter the mass and radius relation in ways that are still being tested. The mass and radius curves have now been pressed from two directions. Heavy pulsars reject rules that cannot provide enough pressure. Compact radii reject rules that provide too much pressure at intermediate density. The surviving path must thread between collapse on one side and an overinflated star on the other. Yet several different forms of matter can still thread that path. Another messenger is needed, one that responds not only to a quiet star, but to a star being pulled out of shape. In August of 2017, two neutron stars spiraled together in a distant galaxy. The signal, called GW170817, passed through Earth as a changing stretch and squeeze of spacetime. Early in the signal, the stars behaved almost like two-point masses. As the orbit tightened, each star raised a tidal bulge on the other. That deformation changed the orbital energy and shifted the phase of the gravitational wave. A stiffer equation of state generally builds a larger star. The larger radius gives the companion more leverage, so the star can develop a larger tidal bulge even though its material resists compression more strongly. A more compact star changes shape less. The accumulated phase shift therefore carries information about tidal deformability, which is another expression of the equation of state. It is like learning something about the structure of a bell from the way its tone changes while the bell is being squeezed, except the squeezing bodies circle each other hundreds of times, and the tone is space-time itself. The gravitational wave did not reveal one unique compression rule. It limited how deformable the stars could have been, and ruled out some of the largest radii that otherwise remained possible. Its strength comes from being independent of surface hotspots. There is no need to decide where an X-ray patch sits, or how its atmosphere beams photons. Its weakness is different. The signal is faint, the late in spiral is brief, and different mass combinations and matter models can imitate part of one another. The result is a range, not an interior photograph. The same event then appeared in light. Gamma rays arrived shortly after the merger. Telescopes found a new source that changed color and brightness over days. Material thrown from the collision expanded, cooled, and assembled heavy nuclei through rapid captures of neutrons. The radioactive decay of those freshly formed nuclei heated the debris and powered the transient glow called a kilonova. Spectra later identified strontium in the ejecta. This was a direct identification of one heavy element associated with rapid neutron capture in merger debris. It did not amount to a direct detection of every heavier element that models predict. In particular, the event should not be narrated as a photograph of newly made gold. The light was shaped by a complicated mixture whose detailed composition, geometry, speed, and opacity had to be inferred. Even that careful statement is extraordinary. A pair of objects formed from collapsed stellar cores carried neutron-rich matter into a collision, flung some of it outward, and created conditions in which new atomic nuclei could assemble. The event connected the pressure inside neutron stars with the chemical history of galaxies. It also repays the imaginary spoonful from the beginning. A piece of core matter cannot be lifted intact and placed on a table. Its state depends on the crushing pressure and weak interaction balance maintained by the entire star. Merger ejecta provide nature's violent alternative. Matter is torn from regions of immense pressure and allowed to expand. As the pressure falls, the material does not remain a permanent nugget of ordinary neutron star core. Its particles react. Neutrons are captured into nuclei, unstable nuclei decay, and the composition changes while the debris races outward. Decompression is not an afterthought. It is the experiment. The evolving light records what matter does after release from the pressure of the whole star. Different portions of the ejecta begin with different neutron richness, temperatures, and expansion speeds. Those conditions decide which nuclei can form and how easily light can escape. Reading the kilonova means working backward through that changing material. So the answer is again a constrained inference rather than a simple sample in a jar. The collision left one question frustratingly open. What object remained immediately after the two stars met? Multi-messenger evidence generally disfavors prompt collapse, and instead points to a neutron star that survived for some time before perhaps collapsing, but its lifetime and final state remain model-dependent. The gravitational wave detectors did not provide a decisive high-frequency signal from the remnant, and the light can be fit by more than one history. And the final state of GW170817 remains uncertain. That uncertainty matters because the remnant sits near the boundary between a supported neutron star and a black hole. Heat and uneven rotation can briefly support more mass than a cold, non-rotating star can carry. As that temporary support leaves, the remnant either reaches a stable neutron star or crosses the mass limit and collapses. Since stable pulsars near two solar masses exist, the cold, non-rotating maximum must lie above them, with only a small rotational correction. A future merger with a measured total mass and a clear collapse signature could show how much higher. The remaining uncertainty is not only where the mass limit lies, it is which material carries the pressure before that limit arrives. The candidate interiors met earlier now face the combined tests. Hyperons or meson condensates may soften matter. Repulsive interactions may stiffen it again. Quark matter may appear gradually or through a sharp phase change. None has been identified directly. This can feel like a retreat after so much measurement, but the narrowing itself is the result. A proposed core must now pass several gates at once. It must support the heaviest, secure pulsars. It must produce radii consistent with pulse profile observations and other constraints. It must not make ordinary merger stars too easy or too difficult to deform. It must permit cooling and rotational behavior that resemble real neutron stars. It must join onto nuclear physics at lower density without breaking what laboratories already know. The useful question is not which exotic word sounds most dramatic. The useful question is what distinct trace each phase would leave. A sharp phase transition could produce a kink or change in the mass and radius curve. Finding two stars with nearly the same mass but convincingly different radii could become important, though surface modeling would need to be controlled well enough that the difference belonged to the stars rather than the analysis. A transition could alter tidal deformability, especially for stars massive enough to place the new phase in their centers. A merger remnant might ring at characteristic frequencies, or collapse on a different schedule. Detecting those features would require stronger high-frequency gravitational wave sensitivity than was available for the first binary neutron star event. Cooling offers another route. New particles can open efficient channels for neutrino emission. Pairing among neutrons, protons, or quarks can suppress some reactions and enhance others over a limited temperature range. A population of stars with well-known ages, masses, surface compositions, and temperatures could separate these effects more cleanly. At present, uncertainties in envelopes, magnetic fields, heating, and ages often overlap the signal of the deep core. Rotation may contribute as well. Sudden glitches show that at least some internal component can store angular momentum and transfer it to the crust. How much is stored depends on superfluid behavior and on how strongly that fluid is coupled to the lattice and charged particles. A very massive pulsar with a clean glitch record could sample a different central density from a lighter one, but connecting a surface timing jump to one exotic phase remains a long chain of inference. The most decisive progress will come from overlap. A binary pulsar may yield a precise mass through radio timing. NICER, or a future X-ray observatory, may constrain the radius and spot geometry of that same star. A merger containing stars in a similar mass range may constrain tidal response. Nuclear experiments can improve the interactions at densities near ordinary nuclei. No one signal has to carry the entire claim. Consider what happens if a future radius measurement becomes twice as precise but keeps the same central value. Several equation of state curves would miss the allowed region. Now add a heavy pulsar slightly above the current secure masses. More soft curves would fail because they collapse too early. Add a merger whose tidal phase points to modest deformation. Overly stiff curves would fail. The surviving strip could become narrow enough that a proposed phase transition either improves the fit across all three or becomes unnecessary. The opposite outcome would be equally informative. Suppose two very precise stars traced an unexpected bend in the mass and radius relation. That pattern could signal a change in the internal degrees of freedom, but only after ordinary explanations such as atmosphere, hotspot geometry, distance, and mass error had been tested. Discovery would not be the first surprising point. It would be the persistence of the bend across independent methods. There is a temptation to ask for one perfect messenger. The star refuses. Radio pulses are superb clocks, but do not outline the surface. X-ray pulses carry compactness, but depend on emission geometry. Gravitational waves feel bulk deformation, but arrive briefly and faintly. Kilonova light reveals expelled matter after it has changed state. Nuclear collisions probe strong interactions in controlled detectors, but they create hot, fleeting matter rather than the cold, old core of a neutron star. The weakness of one method is often covered by the strength of another. Radio timing fixes a mass that X-ray modeling would otherwise trade against radius. X-rays constrain the compactness that a mass alone cannot supply. Gravitational waves test the collective response without seeing a surface. Laboratory measurements anchor the lower density end of the compression rule. The result is not a single window into the core. It is a set of shadows cast by the same hidden object from different directions. No laboratory can make this. That does not mean laboratories know nothing about neutron star matter. Atomic nuclei already contain matter near nuclear density. Experiments with unstable nuclei constrain how neutron-rich matter behaves. Collisions of heavy ions compress nuclear material and test the strong interaction at high density. Particle accelerators create tiny, hot states in which quarks and gluons are no longer confined in the usual way. But none of those experiments assembles a cold, beta-equilibrated, electrically neutral body at several times nuclear density, keeps it there across kilometers, and lets gravity maintain the pressure for millions or billions of years. Cold here is relative to the enormous energy scales of the particles, not a description of how the surface would feel. Beta-equilibrated means that reactions, converting neutrons into protons and protons into neutrons, have reached a balance allowed by the available energies. The small population of charged particles settles into the proportion needed for the matter as a whole to remain neutral. Scale changes the state. A collision can create extreme density for an instant in a volume smaller than an atom. A neutron star creates a stratified, self-gravitating object whose pressure rises continuously toward the center. The outer layers set boundary conditions for the inner ones. Gravity chooses which densities occupy how much volume. Weak interactions have time to adjust the composition. Superfluid and superconducting components can extend across macroscopic regions. The whole star is part of what the matter is. This is why a fragment cannot simply be carried away as a preserved core sample. Remove the pressure and the equilibrium composition changes. Free neutrons outside a bound nucleus are unstable. Dense phases rearrange. Expansion gives reactions new directions. The merger debris of 2017 showed this transformation on a cosmic scale. Matter that had belonged to neutron stars became an expanding factory of nuclei, and strontium left a recognizable mark in the light. Gravity has not pushed matter beyond physics. It has pushed ordinary atomic organization beyond the conditions in which it can remain ordinary. Electron states fill. Captures drive protons and electrons toward neutrons. Nuclei become ever richer in neutrons, then lose their separate identities through much of the core. Quantum statistics, nuclear interactions, and perhaps new particles or quark phases decide the pressure. The result is not matter behaving impossibly. It is matter obeying familiar laws in a regime where familiar objects no longer survive. There is another limit beyond that transformation. Push the total configuration beyond every stable pressure response available to it, and the negotiation ends. A sufficiently massive cold star has no equilibrium radius. A merger remnant may postpone the outcome with heat and rotation, but if it remains above the supportable mass as those aids fade, it collapses into a black hole. Between the ordinary atom and the event horizon lies the neutron star. Its crust can be described with nuclei, electrons, and a lattice. Its deeper crust releases neutrons into a superfluid. Its core contains a dense quantum liquid with a smaller charged component. Its center may remain nucleonic, or may introduce particles and phases not yet identified. The name neutron star captures the direction of the transformation, but not the full inventory. Matter pushed that far becomes a layered, neutron-rich quantum system whose pressure is generated by exclusion, strong interactions, and the composition chosen by weak reactions. It becomes a star, in which a teaspoon-sized metaphor is misleading, because no isolated piece can preserve the state made by the whole. It becomes an object, close enough to collapse, that light bends around its surface, yet stable enough for a radio pulse to keep time across decades. The star itself supplies the apparatus needed to test that answer. A pulsar sends radio pulses through its companion's curved spacetime, allowing the binary to be weighed. Surface hotspots send X-rays along bent paths and constrain its compactness. A neighboring neutron star pulls it out of shape and writes its deformability into a gravitational wave. A collision releases its matter and lets the changing nuclei mark the light. Each signal tests a different part of the same compression rule. The consequence reaches beyond one class of dead stars. The allowed equation of state helps decide which collapsed cores can remain neutron stars and which collapse into black holes, how binary mergers unfold, and how some neutron-rich elements enter the wider galaxy. A measurement only a kilometer wide on a mass and radius plot can alter the predicted fate of objects heavier than the Sun. The larger implication is that inaccessible matter does not have to be unknowable. Nature can maintain an experiment too large, too dense, and too long-lived for any terrestrial machine. Astronomy cannot open the apparatus, but it can watch every way the apparatus responds. The honest boundary remains at the center. Current evidence supports heavy neutron stars near 2 solar masses and a characteristic radius scale near 12 kilometers. It constrains pressure across part of the core and disfavors many proposed compression rules. It does not yet identify the particles and phases at the greatest densities, fix one exact maximum mass, or reveal what survived the merger of 2017. A neutron star is what happens when matter is pushed beyond atoms and beyond any laboratory, but not yet beyond the capacity of physics to test. The core is still hidden. The whole star is how it speaks.